Okay, so let's go ahead and get out the paper that I gave you yesterday. Make sure that you are on the side that has a picture that looks like this, okay? Because that's the side that we're going to be taking notes on. I'm actually going to put this, I have a video here that says light absorption, reflection, and refraction. It's a study jams video, but we're not going to watch it right now. We will watch it. If you get completely done with this activity, I'm going to put that in Edpuzzle as well. So what I want us to remember is that EM waves are going to change their behaviors based on the medium that they interact with. So just like sound waves we talked about, when sound hit a pillow or when sound hit a cliff, it did things differently. Sometimes it reflected back in the form of an echo, sometimes it was absorbed. So light waves will do the same thing, or these EM, electromagnetic waves. There isn't anything to fill in the blank with this screen. I just want you to be aware of what we're talking about. So it says waves do not just stop when they reach the end of a medium or when they meet an obstacle in the path. And it's sort of the same idea that if we have a ocean wave, when it hits a boat, it doesn't just stop. It goes around the boat, or maybe it sloshes up on the boat. And so the same thing can happen with waves. They're going to interact differently depending upon what it is that they're hitting. These behaviors were first talked about when we talked about part 1. So when we said, hey, what does a sound wave do when it hits a cliff? Or what does a dolphin use whenever it sends out a signal? Those are the kinds of things that we're going to be talking about here: absorption, reflection, diffraction, refraction, and transmission, but how it is going to affect the light wave, okay? So we'll watch this video later. I just want to make sure that you get your notes done for these first. So you need 3 color pencils for this. We need yellow, green, and blue. So I need you to go ahead and get those yellow, green, and blue. And you should see this picture in the very top right-hand corner of your notes. So what we're going to do is we're going to talk about 3 main types of behaviors that the sun's interaction allows life to live on Earth, okay? So the first and foremost, and what you're going to do is you're going to find the bubble on your paper that says transmission, okay? You're going to highlight that bubble yellow. So find the bubble, it's right down below where we're going to be taking notes, and it says transmission. Anything I highlight on this picture is going to represent transmission. So the sun is in space, and the sun is transmitting. Here we go with the highlighting. The sun is transmitting its rays to the Earth. And it's not just light rays. It's radio waves, it's gamma rays, it's ultraviolet rays. It's all those waves that we haven't necessarily talked a lot about yet because we missed out due to the snow, and so we've lost a little bit of class time. But we'll get caught back up. But it's these behaviors. So transmission just simply means that it's passing through a region. So notice that I'm not going all the way down with these yellow lines. I'm stopping right here at this gray area on my screen. That gray area represents the atmosphere. So what happens when these rays hit something? Because remember, they've been traveling through space. There's a lot of emptiness, meaning a lack of atoms or lack of those particles, and so there's nothing to interact with them. They're traveling at the speed of light. But then they interact with our atmosphere and they slow down. They don't speed up like sound waves do, so they slow down. And when it hits the atmosphere, we are going to change colors here. Sometimes we are going to start seeing some of these things be absorbed. So I'm going to change colors. Some of these are going to be absorbed by the water vapor that is in the air. So you think about all the evaporation that has taken place. In that evaporation, all those little gas water molecules are up there. Some of this that is transmitted is going to be absorbed by the Earth's surface. So whether it is actually the land, or whether it's the water, or whether it's the road, or whatever it may be, your house, you for that matter, some of it's going to be absorbed. Okay? But then some of it's also going to be absorbed by another thing that gets in its way, which is the cloud. So there's lots of things that can absorb this material. So don't forget to color your bubble on your diagram there that in green as well. So yellow is transmission, green is absorption. What happens though if it doesn't get absorbed by the Earth? It's going to end up getting reflected. So we're going to change to a blue, and I don't care what color blue it is, light blue or dark blue. But what we're going to look at here is that sometimes these rays are going to get reflected back. when it gets reflected back, sometimes this energy leaves back into outer space and doesn't go, it doesn't stay within the Earth itself. So it can get reflected by the clouds, it can get reflected by the Earth, it could actually get reflected by some of those little tiny water vapor molecules and other gases that are in the air as well. Those are the three main ways that we look at rays that actually get through our atmosphere, and sometimes how they don't stay, they go back into space. Remember, gamma rays are not going to do this, okay? Gamma rays don't make it through. There are other rays that do not make it through our atmosphere, and that is extremely helpful because we don't want to die from them, okay? But these rays, when they do get through the atmosphere, this is what happens with them. Okay, so these are the three biggies. There is one more that is not mentioned in this picture, but we will talk about it. It's refraction. So let's go ahead and talk about transmission first. Okay, so this is, remember, the bubble that you should have highlighted in yellow. So if you haven't already done that, please do so. Now, the very first thing that you see right here, this is the definition of transmission. So I want you to write that on your paper where it says DEF. That's where you write the definition for each one of these behaviors. So the definition is the passage of EM waves, the electromagnetic waves, through a medium. That medium, in this case, we're looking at right here, is glass. Okay? What happens when it goes through, or what happens when it hits it? What we see here is that when this light ray hits the glass, it continues to go in the same direction, okay, and it exits out the other side with the same intensity. That's what we consider something to be transparent. So you need to use this word to fill in the blank, and when we say something is transparent, it allows most of the light to go through. And this is that idea. Here are the incoming, or those incident lights, meaning that they're coming inside, and then this is what happens when it leaves it. So I look at out my window right now and I see that transparency. I can see what's out there, people can see me, they're looking in here, and that's the idea. It doesn't change, it's still going in the same path. But if something is translucent, okay, something is not going to allow all the light through, it's going to end up scattering it. So if you look at this picture right here, we're looking at that idea of the light coming in, but then it going in multiple directions, and it's not allowing me to see what's on the other side. A lot of times I use these kind of windows in a bathroom to where you can't see what's going on. Either way, light can still pass through, but it's not going to give me enough to see what the images are on the other sides of those windows. And then finally, the third thing, if something is opaque, this is the idea of it being opaque. It goes into it, but there's nothing outside of it. It gets absorbed, okay? So when we talk about this, you're saying, well, this is an absorption idea. I agree, but it's the idea that nothing gets transmitted and nothing goes through. That's what we consider to be an opaque material. So here's what I need you to do. I gave you a half sheet of paper with pictures on it. Okay, I want you to find the two pictures. This is picture 1, this is picture 2, and I want you to label those as transmission, because when you get completely done with this video, you're going to cut these out and then you're going to glue it onto your notes that says examples and illustrations. Instead of us drawing, we're going to cut and paste. Okay, so that's going to be what you do after you get completely done. So don't forget to find those pictures, otherwise you're going to have to go back through. Okay, absorption. We looked at that a little bit when we talked about something being opaque. So you should have already highlighted this in green for your bubble, and we talked about how the atmosphere was absorbing some of those rays. And when we talk about absorption, we're looking at the transfer, here we go, of light energy into a medium. Is it going into a cloud? Is it going into the ground? What is it going into? Okay, and depending on what it does go into, it can actually make things feel warmer. Okay, and how does it do it? By absorbing more energy. So those rays are carrying a lot of energy depending on what kind of ray it is, and depending on the actual color of something. So for instance, this one picture that you should be looking for says, hey, what happens if I have a white surface? It says that I end up getting a reflection of a lot of light and nothing is getting absorbed. So this shows no absorption. But then if I look down here in this picture, okay, it shows all of my light getting absorbed. So this is showing absorption, 100%, okay, of absorption. And what this means is that there is no light reflected. And so when I look at these two pictures, on a hot summer day, I would much rather be stepping on a white, cool surface versus a hot, pavement, black pavement, because what I'm going to do is burn my feet. And why am I going to burn my feet? Is because that pavement, having absorbed all of the colors of the rainbow, all of the colors of what we consider white light, and not reflecting anything, meaning it's not reflecting any energy back, it's holding all the energy in, it's keeping my foot extremely hot. And so that's why I wouldn't want to step on that pavement. Whereas a white surface is reflecting it all back, and it's not keeping it in by absorbing it. So that's why things are actually going to feel warmer or cooler. Another thing that absorption has a great deal to do with is why we see the colors that we do. When we talk about seeing green or seeing black or seeing white or seeing red, whatever color that you see, it's because it has absorbed every other wavelength. Okay, we say color, but typically what it actually is, when you were in elementary school, wavelength was too big of an idea, so they said color. What our eyes are visualizing when we see red is a certain wavelength, and red has the longest wavelength. So what we see here, and you can color this in on your picture too, red, okay, orange, yellow, green, blue, these are the colors of the rainbow, Roy G. Biv, if any of you are familiar with that, and I'm going to skip over indigo and violet, okay? It is absorbing everything except for this guy right here. This guy is why we see green. It's because it gets reflected. Green gets reflected. You're like, oh, but this is absorption. I know. It absorbs all the other colors, and then it reflects that green back to my eyes. Okay? When we look at this picture over here, we look at it absorbing every single color of the rainbow. Red, orange, yellow, green, blue, indigo, and violet. And it reflects black. So when I see a color, it's what is reflected and not what is absorbed by that object. So make sure that you find these pictures, okay? And this is going to go underneath absorption, along with the pictures from this slide right here. So make sure you're always finding your pictures, write absorption next to it so we can cut it out and paste it at the end. Next, we have reflection. Reflection has a lot of things that go with it, and we all know that we can see a reflection in a mirror. But depending on the kind of mirror that we have, that can vary. Okay, so really what we look at with this guy here and the polar bear, he is directly looking into what we could consider a mirror. So reflection is when light waves are bouncing off of a surface, much like my sound waves are bouncing off of a surface causing an echo. And that sound wave comes back to me. In this case, my light wave comes back to me, and I see myself in something that is a reflection. So that's why I can see myself. Now sometimes, depending on the angle that it hits at, I might not see myself straight on like this polar bear is. And you can sort of see what happens if this polar bear weren't looking at the smooth surface into the smooth surface of water. Smooth surfaces allows light to be reflected significantly back. And as you can see, this flashlight hits this mirror right here. And when it bounces back, it gives this nice light down at the bottom. So this is a nice smooth surface, much like we see right here. And that's what this picture is trying to say. If the light comes in at an angle, it leaves it at the same angle. So we call this idea of parallel reflection, that the light bounces off and back into waves that are parallel to one another. So if this is a 20-degree angle, this angle would also bounce back at a 20-degree angle and reflect back that light to you. Now, down in this picture right here, what we see is that we don't have, and I'm going to try to use a yellow here, we don't have, this is hitting a piece of paper. It's not a mirror, it is a rough surface, and you can see that this light is very diffuse. It is much more scattered, it's not as direct as we saw in the picture right above it. So notice what happens over here. Some light goes one way, some light goes another way. There is no specific angle at which they come in at and they go back out at. It is all sort of a scattered idea. And that's why the light looks scattered, is because it's not in a parallel reflection like we had in the top picture. If you have ever looked at a body of water and you've seen, you know, like in this first picture here, a mountain range, and this mountain range looks really beautiful in the water, and you're like, hey, that's, you know, what's going on here? But then we look at a wavy situation where there's not a still surface, it is disrupted, it is a rough surface, and when we talk about rough surfaces, we get that diffuse reflection. We get rays bouncing back, and that's why we don't see a beautiful reflection like we do in something that has a smooth surface. So smooth versus wavy, rough surfaces, something that is not going to be a good reflector is going to cause a lack of reflection. It scatters the light. Then we can talk about reflection using different shaped mirrors. And if you've ever been in one of those mirror mazes and you look upside down, you look really skinny, you look really big. I mean, you look like all different things. And they all do that based on the kinds of mirrors that they're using. So concave versus convex. If you'll get a spoon, and this was something that I had planned on doing with you, but if you'll get a spoon when you go home and you look out one side of the look at yourself in one side of the spoon, it's going to give you a concave look. You're going to look at yourself, and it's going to be the same image reflected right back to you. But then in the convex, what ends up happening is it flips it, okay? And you're upside down on the other side of the spoon in the convex. So do this at home. I'll let you do this as well whenever I come back, but do this and you'll quickly realize, oh, wow, I never really realized that maybe. So there's lots of uses for concave mirrors. Find these pictures because the dentist uses this, you use this whenever you look into a magnifying mirror. Lots and lots of different uses for these concave mirrors. But then I look for the picture that has examples of convex mirrors, and these are typically those rounded type mirrors that you're looking at when something looks really, really far away than it should be. And we use this on our vehicles. We use this to see if something's coming from way down the road, in a security security area in a store, that kind of thing. So reflection and just how that object is shaped is going to change the way that it looks to you. Last but not least is refraction. So key idea here, the definition, when light bends, it changes speeds, and so when it changes speeds with light, it really looks odd. It looks like something is broken or bent where it shouldn't be. And so things can get extremely weird looking, and this, when we do a lab, you're going to see some of these things that are really cool due to refraction. So, you know, we see back in the time where we would have had to have fended for ourselves and gotten our own food, it would have been sort of difficult to know where exactly are you supposed to stab for that fish if you didn't keep this idea of how refraction worked. So we actually look at the image being here, but this is what we're trying to figure out is where that fish is. So it bends it. That light bends when it hits water. It changes speed. Remember, we're traveling at the speed of light in the air, but when it hits the water, it slows down. And so it doesn't continue to go through the water the same way that it would have through the air. Well, that causes us to see stars in the sky very, very differently as well. And so where we think a star is isn't the actual place, it's the apparent location. And so once again, it sort of is an optical illusion. Our moon looking really, really, really large on the surface when it first comes up on the horizon, or when it goes and gets ready to set in the evening, or when it gets ready to set, I shouldn't say in the evening, sometimes it's in the morning. But when the moon looks really, really large compared to when it's up in the sky, once again, this is sort of that idea of how light is being refracted because it travels a lot further on the edges of the horizon than where it is directly up in the sky. And so it looks like it's bigger, but it actually isn't. It is the exact same size, and if you take your pinky, you can sort of measure it with your thumbnail or your fingernail and look at it whenever it is on the horizon, and then take that same distance or that same length with your fingernail and put it up into the sky when it's right above, and you're going to see it's the exact same size. So an easy way to sort of see, hey, it's not really changing. And then when we're looking at the idea of how we can actually use this to think about the light itself and what happens when it does get refracted, we can look at the idea of white light and using a prism. And when it hits a prism, it basically bends those light rays to where we can see all the different colors in the spectrum. So typically white light, if we're looking on a nice sunny day, we see that white light of the sun. But if we had a prism, we can actually cause it to change into red, yellow, all the Roy G. Biv, basically all those colors that we think of in the rainbow. So all wavelengths are always visible in that light if we have a way to get it out. And a prism is one way to do it. And that's what we're talking about right here. When it hits that edge, when it hits that medium that is different than the air, remember this is the air, and then it hits this prism medium, it changes from that white light. It basically bends those rays apart and spreads it out into the different wavelengths that make it up. So that's what we call refraction. It also can hit a raindrop and do the exact same thing. And when it hits the raindrop, we get to see a beautiful rainbow. Okay? And so what the prism is here is that idea of the raindrop. And I've talked a little bit about this to some classes depending on how far we got, but I want you to look at this idea with the color red. Why is red at the top of the rainbow? Because it is the longest wavelength. And when we talk about electromagnetic spectrum, we'll go back and look at that. And it has a much longer wavelength than something that is this violet color, which has a high frequency. It has more energy, which means it has a shorter wavelength. And look at where it is on the rainbow. So why is it ordered that way? It has everything to do with how long their wavelengths are. Okay. So this is the last slide that we have right here, and talking about refraction. And so anything that basically has a lens in it, including your eye, a microscope, a telescope, many other things in our world around us, all are going to be examples of things that are going to refract light. So I'm hoping that you went along through this and that you made sure you've identified all the pictures. Otherwise, you're going to have to go back for the video and do that. At this point, whatever time you have left in class, I want you to go ahead and cut those pictures out, paste them, glue them, and if you have any extra time after that, just make sure you follow the activities that I have provided you. Have a good weekend, guys.